Welcome back everyone. In this video, I will be discussing the basic principles of chromatography. Hopefully it won't take too long because this is mainly a revision for all of you. Now, before we start, I just want to go back to this slide which summarizes the analytical techniques in chemistry that we cover in VCE. So when you look at an analytical technique, the first thing you want to ask yourself is it a qualitative technique or is it quantitative? So what is the end goal here? Now, a qualitative technique really focuses on finding the identities of chemicals. So the flame test, which was one of the first things that we show you, not very specific and not that accurate, but it can give you an idea of what kind of metals are present in an ionic compound. Mass spectrometry sadly has been removed from this year, but you've learned this last year and it actually does have a qualitative purpose. The three techniques in red are the one that you need to know for year 12. So the first one is the chemical test. So we're talking about things like the bromine test or oxidation with chromium or even reaction with metal carbonate. So by doing those chemical tests, you can gather information on the identity of the chemical. And this is what IR and NMR spectroscopy both fall under. They are both qualitative techniques. Today we're going to start looking at quantitative techniques. And the purpose of a quantitative technique is to determine the concentration of something. Now, there are 5 quantitative techniques that you have seen. I don't know how much you remember the last 2, but in year 12, we only need to focus on these 2, which are volumetric analysis or titration and chromatography. I do want to point out that chromatography is unusual in the sense that you probably can also consider it a qualitative technique. It does have an ability to allow you to determine the identity of a substance, but it's not as good as infrared or NMR spectroscopy. So it relies on the existence of a standard, which I discuss in a bit. All right, so let's talk about principle of chromatography. Now, the first thing to remember is that these techniques, the whole point of this technique is to separate molecules in a mixture. So you would use chromatography if you have a mixture of some things and you want to know what are the molecules in that. So it is very good to analyze mixtures such as ink or blood or urine, or I think even in terms of gas chromatography, you can use it to determine the compositions of air quality in different places. So whenever you have a mixture, which you most of the time have a mixture in everyday life, and you want to separate the mixture into its components, you would use chromatography. So all methods of chromatography would have a stationary phase and a mobile phase. And let's talk about the phases first. So stationary phase, you probably don't have to write these notes down. I think everyone remember the stationary just means it doesn't move. So this is the immobile surface that the different components of a mixture can adhere to. And the process of sticking or adhering is called adsorption. Emphasis on the letter D here. So it's adsorption, not absorption. It's not absorbing into the surface, it's just adhering or sticking onto the surface. So that's the stationary phase. The mobile phase is a solvent. So it could be a mixture as well, usually a liquid or a gas, depending on the technique, that will carry the components along the stationary phase so that they can separate. And the process of detaching from the surface of the stationary phase is called desorption. Now, you don't necessarily have to use both adsorption and desorption when you explain what's going on in chromatography. Most of the time, adsorption is enough, but desorption is just the opposite of that. So you need 2 phases, stationary phase and mobile phase. All right, so this animation, I don't think it's an animation. This diagram, it's another explanation of what actually happens in chromatography. So this is a stationary phase. Now, so if you think about this, this is going to be the origin, and this particular diagram is just drawing what is going on sideways. But if you're looking at paper chromatography, obviously you're supposed to have the paper in this particular orientation. So adsorption is to stick onto the stationary phase. So you're going to have a surface and the mixture, or the substances in the mixture will either adsorb to the stationary phase. Now, stick is a very cute word in year 11. If you are in year 12, I would expect that you can give me a little bit more information about what actually causes the molecule to stick to the stationary phase. And in the majority of cases, it's probably going to be some sort of intermolecular forces. There are other more complicated issues that can happen, but you don't have to worry about that in BCE. So the reason why it sticks onto the stationary phase is due to intermolecular forces. Okay. And to unstick or to dissolve is just when you want to get out of that surface. So when a mixture travels across the stationary phase, it's going to stick onto the stationary phase due to forming different ranges of intermolecular forces, and the strength of that will allow the separation to occur. And I think I actually have the component. Yeah, so it rises up, or in this case, it goes to the right, and the degree of adsorption, it's going to cause the separation. All right, so I think that basically summarizes what I just said. Different molecules would have different degrees of adsorption and desorption, or you just have to focus on adsorption. Because they have different degrees of adsorption, they would travel at different speeds across the stationary phase, and that's how they are separated. Now, if we are focusing on a general principle of chromatography, then I think it's better to say that they travel at different speeds. It's probably not appropriate to say whether they will travel at different distance or different times, because that really depends on the chromatography technique that you're using. But they definitely will travel at different speeds if they have different degrees of adsorption. And the last thing I do want to point out, this is probably the main one that I want to focus on in year 12, because the basic principle is very simple. I mean, you learn some of this in year 10, is that these differences in degree of adsorption are due to the different sizes and compositions. The main one we're going to look at in year 12 is polarity of the molecules. So because you are at a higher level in your chemistry education, you may need to be able to predict or explain why they have different degrees of adsorption. So let's talk about that. Now, the first thing, which I think it's very obvious, is that molecules with larger masses will often, let's actually spell things correctly, often travel more slowly. So I think that's self-explanatory, but if you want, you can also talk about intermolecular forces here. Larger molecules have stronger dispersion forces with the stationary phase. So you have stronger dispersion forces, or you can just say if something is rising up, it's going against gravity, so if it's larger, it's going to be harder to do that. I'm not going to go into gravity and everything, but if you need an explanation, you can use dispersion forces. Larger molecules have more electrons, so they can form stronger dispersion forces with a stationary phase. And the other thing has to do with polarity. So nonpolar molecules would be more attracted to a nonpolar phase, and polar molecules would be more attracted to a polar phase. So I think this is pretty obvious as well. So this is very similar to the like dissolves like rule that we learned in year 11. Nonpolar substances like nonpolar substances, and because they can form strong dispersion forces between them, whereas polar substances would like polar substances. Now, the type of intermolecular forces that you can have between polar molecules would depend on the molecule, so you can either have dipole-dipole interactions or hydrogen bonds. And you bet that I would ask you to identify which one based on the situation. All right, let's give you a few examples. So the first thing is, in order to predict the degree of adsorption, you need to know the nature of the stationary phase and the mobile phase. So I'm actually giving you that information here. So let's read the question together. Yeah, because there's some other people here beside me. Consider a chromatography technique that has a nonpolar stationary phase. So the stationary phase is nonpolar, and a polar mobile phase. Probably should say mobile and not stationary twice. So nonpolar stationary phase and a polar mobile phase. A mixture of the following molecules is separated using this technique. Order the molecules from least adsorbed to most adsorbed. So least adsorbed, the one with the lowest degree of adsorption, would be the one that is most polar in this particular situation. Because the stationary phase is nonpolar, the one that is the most in the opposite version of it, it's going to be the least adsorbed. Or you can say that the most polar is going to be the one that is most attracted to the mobile phase. And the one that is most adsorbed is going to be the most nonpolar. However, this can change if the nature of the stationary phase and mobile phase change. So don't assume that the stationary phase has to be nonpolar. Sometimes it's not, and that's when students who don't read the question get it wrong. All right, so there are 3 molecules. Now, it's normally not fun if the 3 molecules are of different sizes, because the size also plays a factor. So if you look at this, I actually am regretting this. I think what I'm going to do is, okay, so this one is smaller. So C is going to come out first because it is the smallest. So this C is going to be the smallest, which means that it's going to be the least adsorb. Also, it is polar as well. It has a hydroxyl group here. And then you're going to have either A or B. Now, B is a carboxylic acid, so it is more polar than A, which is an ester. So it has a carboxyl group here. And the carboxyl group can form hydrogen bonds, so it is the more polar group, whereas this one, which is the ester, can only form dipole-dipole interaction. So the ester is going to be the most nonpolar out of the three examples, and it's going to be the most adsorbed. It's always funny when you ask students to do an ordering question, they always get the order the other way around. So sometimes I make that mistake as well. So it's really important to read the question very carefully to know whether you're going from least adsorb to most adsorb, which is the same as going from polar to non-polar in this particular case. All right, let's do another example. So let's hope that I actually get the number of carbon right this time. So this is a very interesting example because they all non-polar and they all hydrocarbons. So the only difference between A, B, and C in this case, my stationary phase and mobile phase remain the same as the previous example. So I have a nonpolar stationary phase and a polar mobile phase. But if you look at these three molecules, they all have the molecular formula C6H14. Or you can just trust me that, so you don't have to count yourself, but they are actually structural isomers of each other. The only difference between them is the branching or the length of the longest carbon chain. So A has two branches, B doesn't have any branch, and C has one branch. So the question is, if they all nonpolar, how do you determine which one is going to come out first? Which one's going to be the least adsorbed to the most adsorbed? And the answer to this is actually very similar to the effect of stacking, which we talked about as something that affects the ability of a molecule to form intermolecular forces. If something is a linear chain, it's going to be easier to get very, very close to the nonpolar stationary phase and form strong intermolecular forces, in this case, dispersion forces. So if something is is linear, like in this case, it is going to be easier to form dispersion forces. The more branches a molecule has, the harder it is going to be to get close to the stationary phase and form dispersion forces. So in this case, A is going to be the one that is the least adsorbed because it has two branches, so it will be the most difficult to form strong dispersion forces with the stationary phase. So I would actually start with A being the least adsorbed. It's going to follow by C, which contains one branch. So A, C, and then B is going to be the most adsorbed because of the lack of branching, allowing it to form stronger dispersion forces with the stationary phase. So stacking does play a role in predicting the degree of adsorption, very similar to the effect that stacking has on melting temperature and boiling temperature. Now I do want to say, so this one is pretty obvious. Like if you want to optimize the separation in a chromatography technique, you want the stationary phase and the mobile phase to be opposite of each other. So obviously if one is polar, you want the other to be non-polar. The stationary phase doesn't have to be the non-polar one though. There are different types of techniques and I don't want to generalize here. Now, in some cases, the size of a molecule and its polarity might lead to contradicting interactions. So you can have something that is very big, for example. This one's probably not that big in retrospect. I mean, if you think of a lot of macromolecules, they are a lot bigger than this. Or if you think about sugar, which is a pretty big molecule, size of 180 grams per mole. When by sugar, I mean monosaccharide or glucose, but it actually is also incredibly polar. If you have a non-polar stationary phase, it will like the molecules that are larger, but then if it's polar, then is it going to come out first? Is it going to be more adsorbed or less? The answer is it's going to be very hard to predict in those situations, and you're probably better off just run the experiment and see for yourself. So I don't think you're going to be asked to make those predictions if the molecule are hard to predict because they're very big but also very polar. or very small but very nonpolar. Actually, the one that's small but nonpolar tends to come out first, especially if you get a gas. So don't worry too much about those situations because the prediction doesn't work every single time. All right. Yes, I said that already. So that's the end of this video.